All right, so this one it'll be a shorter one. Hopefully, and I'm doing 4, 5, and 6. Number 4. First, I'll circle the answers for you on these, but 4, 5, and 6 is D, B, and A. Okay, so to work out number 1, number 4. Determine the charge on oxygen in the radical species ClO with a dipole moment of 1.24 Debye, and dipole moment we know is that, and a bond distance of 1.57 angstroms, and that's going to be our R, right? So we know we're going to be solving for Q here, just like we did on problem number 3. Since I worked it out last time, we know that Q is going to equal that divided by that. I'll work it out real quick over here to show you from the original problem. We know it's this times this, and then divide by R, you get that. So apparently I can do chemistry, but I can't draw an arrow. Anyways, Q equals dipole moment divided by the radius, or the distance. Okay, so we're given that. So we know we need to convert the dipole, or the debye, into Coulomb meters. So we'll do that. U equals 1.24 debye times 1 debye is 3.336 times 10 to the negative 30 cm, and that is going to equal, drawn everywhere, 4.137 times 10 to the negative 30 cm, because that cancels, right? And that's Coulomb meters. R, we're going to have to go from angstroms to meters, so our Coulomb meters will cancel. So let's go ahead and do that. 1.57 angstroms is 1 angstrom, 10 to the negative 10 meters, right? Bow. 1.57 times 10 to the negative 10 meters. Solving for Q, we'll change colors on you here. We'll take this one divided by this one. So draw my line. 1.57 times 10 to the negative 10 meters. Sorry about that. I'm popular right now. 1.37 times 10 to the negative 30 meters, and bow. And then I'm going to go ahead and add in the step just like I did over there, so I don't have to solve for it again. Coulombs. 1 electron equals 1.6022 times 10 to the negative 19 coulombs. Bow. So Q is going to equal, when you math, random color, all right. That divided by that, oh, I did this during SI too. That's 30, not 3. So negative 30 minus negative 10 is going to equal negative 20, right? And then so negative 20 minus negative 19. I'm just working out the exponents, but you can do this in your calculator. Your answer is going to be 0.164. Now check and make sure everything's in 3 sig figs. Yep, 3 sig figs, 3 sig figs. And that's our answer right there. That's what the charge on the oxygen will be. All right. So this one is more conceptual here, but the first thing I would do when looking at these is I would make sure everything at least has an octet. So sulfur, 2, 4, 6, 8, 10. When you see more than 8, you want to check and see if it's period 3 or below. Remember, period 3 on, period 3 and plus can do an expanded octet, meaning that it can hold more than 8 electrons. So we have 10 in this case, so that's fine for now. Fluorine has 2, 4, 6, 8. Happy, 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 happy. So far, that seems good. Oxygen right here, 2, 4, 6, 8. Happy, 2, 4, 6. Not so happy. Actually, it's kind of mad. Let's make it mad. 2, 4, 6, 8. Happy. So within this guy right here, he's like, man, that's not fair. So we know so far B isn't correct, but let's keep moving. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12. So it's period 3 and below, so that guy's all right. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All happy. This one right here, so we have the charge, so we're okay there. 2, 4, 6, 8, check. 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 And look at that, everybody's happy. This is one of the resonance structures, by the way. Another way you could write this is bop, 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 O, 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 dot, 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 dot. And you're not going to draw the electrons if you do it in this case because of the fact that you're showing the resonance structures. And that's just a generalization of all the resonance structures. In this case, your charge is going to be on these two. So let me draw one more time for you. Just bear with me here. O dot 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 dot. Oh, this is not a good drawing. But this gets into formal charge here. So this 2 minus. So formal charge, valence minus lines minus dots. So in this oxygen, we have 6 for the valence, 2, 4, and there's 2 lines, so 6. So 6 minus 2 lines minus 4 dots equals 0. So that's charge on that. This one right here, 6 minus 1 line minus 6 dots. It's going to equal -1. So we have a negative charge there. And since this is the exact same, negative charge. Carbon, 4 valence. 4 minus 4 lines. 1, 2, 3, 4. Minus 0 dots is 0. So no charge. So you'll have the 2 charges there. So basically the one without the double bond is going to have your 2 charges. That's just quick side note there. So for O3, let me switch up colors, and I thought this was going to be a fast one, but apparently not. So start off by drawing your bonds. You got 3 bonds, and you have a total of 18 electrons, and we've used 2, 4 of them, so that leaves us with 14. So let's go ahead and go 1, 2, 3, 4, 5, 6. So take away 6, 14, so that would be 8. We only have 8 here. So I'm going to go ahead and go 1, 2, This is honestly just from experience. That and it's right there too. So 8, 2, 4, 6, 8. So that gives me everything I need right there. Right? So 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons. That's the correct charge. That one's missing this lone pair right here. See it? Not there. That's why he's not happy. Already at 10 minutes. Damn. Sorry, guys. Okay, new color. Alright, so ionization energy. And we're talking about copper here. If we're talking about the second ionization energy, number one, for ionization energy, we want, for IE, the electron is going to be on the right. For EA, or electron affinity, the electron is going to be on the left. I remember it like this. For the left, we have electron affinity. So you have LE, and then for the right, we have ionization energy, RI, right? And so that's how I remember it. So just by looking at this, we're talking about ionization energy. We need to make sure that the electron's on the right. So we can get rid of that. Electrons on the left there. Okay, so if we're talking about second ionization energy, that means the first one's already happened. The first one's already happened, we've already lost one electron. So copper is going to have a positive charge. So if we look on the left here, copper has a positive charge. Copper does not have a positive charge. Copper has a positive charge. So, and you're going to be talking about these in gas. We know electron's going to be at the left. And so here's what we got here. These are our two options. And Cu, undo that, Cu plus gas plus electron. Now the reason that this guy right here isn't right is because number one, the charges are wrong, right? Positive 2 on this side, and over here, +1 plus -1, that equals 0. And you can't just make up stuff. You can't have charges just appear out of nowhere, so that's incorrect. So you can eliminate that. But when it's talking about the second ionization energy, that means the first has happened, like I said. So we've already got one positive charge here, and then when you lose another electron, you'll go to a +2. That's why the answer is A on that one. So sorry this video was longer. I'll post another video soon. For the rest of them, I just got to do some of my homework real quick.